dia, pessoal. Good morning, everybody. We're here to present David Santiago Quevedo. Thank you, David. And he's got his bachelor and master in theoretical physics at the National University of Colombia. And now he is a PhD candidate at Utrecht University, working with Cristiani, who presents for us on Monday. He works with statistical mechanics, econophysics, and complex systems. Again, David, thank you so much to present for us. And you will put his video now.
Thank you. Good morning.
Good morning.
Hello, everyone. Thanks for attending this talk. My name is David Santiago Quevedo. I'm a second-year PhD student in the Institute for Theoretical Physics at Utrecht University. Today, I'm going to talk about anomalous diffusion and emergent time order in the fractional Langevin equation with white and color noise. The results from this work were obtained together with my colleague Robin Verstraeten under the supervision of Christiane Moraes-Smith. You can use this QR to go directly to the archive preprint and check a bit of the details on the results. So let's start with the fractional Langevin equation with white and color noise. So this equation describes the motion of a particle under the action of two random forces, F1 and F2, and two dissipative forces, one with first order integer term and one with a fractional derivative term. So by definition, the white noise has autocorrelations in time proportional to a Dirac delta with an amplitude θ1 that depends on the physical characteristics of the systems. And the color noise has power law type correlations with amplitude θ2 that depends as well on the physics of the system. Both forces are centered around zero. And the fractional dissipative term is defined in terms of the Caputo definition of the fractional operator for alpha between 0 and 1. The system can be described from a microscopical point of view using an extension of the Caldera-Leggett model for quantum open systems. So for this, we assume that the particle M is coupled to a set of harmonic oscillators that compose a thermal bath. So in particular, we assume that we have two thermal baths, one with temperature T1, with global temperature T1, and the other with global temperature T2. So the dynamics of the system can be described by this set of Lagrangian terms. So the first one is the Lagrangian of the particle, which contains the kinetic energy of the particle and the potential energy. The second term is the Lagrangian of the baths. So we see that we are summing over the two baths. We assume that these baths are independent and they contain the kinetic energy of the velocity and the kinetic energy of the oscillators. And we have a third set of Lagrangians that are the interactions, which are here highlighted in green. So the first one is the Lagrangian for the coupling between system and the bath. The coupling is made through the position coordinates. And a fourth Lagrangian that it's a contour term that it's used to cancel out certain additional terms that emerge after solving the Euler-Lagrange equations and coarse graining the system. So when we solve the Lagrange equations, we can coarse grain the system in different ways. So we studied two cases. The first one is an inequilibrium noise case in which the spectral functions are defined in two ways. So for the first path, we assume an ohmic spectral function, so a linear function in terms of the frequencies of the system, and a second non-ohmic spectral function that is proportional to omega to the power of alpha. We assume that the temperatures of the baths are in equilibrium, so T1 equal to T equal T. And then after solving the system, we find that the amplitudes of the noises are, for the white noise, 2 eta1 kVt, and for the color noise, eta2 kVt, where eta1 and eta2 are the dissipative constants introduced in the spectral functions. So we find that kind of trivially, gamma is equal to theta1 and zeta is equal to eta2. That means that the white noise is contributing to the white noise force. So the first bath, sorry, is contributing to the white noise force and to the linear dissipative term. And the second thermal bath is contributing to the color noise and to the fractional dissipative term. So in this scenario, we can identify a memory kernel for the system that it's a superposition of the Dirac delta function and the fractional memory kernel in the dissipative fractional term. And we observe that fluctuation dissipation is preserved, is satisfied. So that means that the correlations of the total force F1 plus F2 are equal to KVT times the memory kernel of the system. We can observe this easily directly from the equations of the correlations. And we also studied an out of equilibrium noise case in which we assume that both baths have non-ohmic functions. So they have the second function that we defined for the previous case, which is proportional to omega to the power of alpha. But since we want to preserve white noise emerging from one of the baths, we need to introduce a thermal gradient for the first bath. So that means that we are assuming a local temperature associated to each degree of freedom of the bath, that it's proportional to the frequencies of the bath. And we also have to introduce the length scale of the system, this T sub alpha, in order to keep the units of the temperature correctly. So after coarse graining the system in this way, we obtain that the amplitude of the white noise is affected by this length scale of the system, but it's pretty similar to the first one. And the amplitude of the second bath is the one that we obtained in the past because we are not changing anything in the second bath. But interestingly, we also obtain that in this case, gamma is equal 0. That means that we get rid of the linear dissipative term, and both baths are contributing to the fractional dissipative term. So this has interesting repercussions in the physics of the system, as we will see in the results. But the first one, the most evident one, is that fluctuation dissipation theorem is not preserved anymore. However, we can still find a relationship between the second bath, the one that it's generating color noise, and the fractional dissipative term. So it can be used actually in order to obtain analytical solutions for the mean square displacement, as we will see in the next slides. So we studied the system using both analytical and numerical methods. So for the side of the analytical solutions, we used the Laplace transform technique, as usually in physics, in order to obtain solutions for the position and the velocity of the system. So the solutions of the position are obtained in terms of the relaxation function capital G, and the solutions of the velocity are obtained in terms of the relaxation function of the velocity, which is nothing more than the derivative of the relaxation function of the position, the derivative in time. So we can come back from the Laplace transform space using the convolution theorem and obtain expressions for the relaxation function of the system in terms of the Prabhakar-Mittag-Leffler function. This is a generalization of the Mittag-Leffler function, which is in 3 parameters. It has 3 orders, and the third one basically affects the combinatory characteristics of the function. We can also obtain analytical expressions for this memory kernel when taking the limit of zero friction, zero linear friction. When we take this limit, we observe that only the degrees of freedom, the orders k equals 0 of this Prabhakar-Mittag-Leffler function contribute to the system, and then we can reconstruct a 2-parameter conventional Mittag-Leffler function using the contributions from this zeta m. So we see that the first dependence in the first general relaxation function was in terms of gamma over m, but then here for the relaxation function of the zero limit friction case, we have a Mittag-Leffler that depends on zeta over m. This is because we reconstructed this Mittag-Leffler using the part outside the Mittag-Leffler in the expression of the relaxation function. We also implemented a numerical recursive scheme in order to obtain numerical solutions for the system. To do so, we use the fractional Brownian motion to model the forces. So we model the first force, the first random force, as proportional to the increments of a conventional or ordinary Brownian motion, and the second random force as proportional to the increments of the fractional Brownian motion, where the fractional Brownian motion is defined in terms of the Horst exponent, this h, that gives you how the correlations evolve in time for the increments of the motion. So if h is equal a half, we have conventional Brownian motion. So that means that we have independent increments. If h is smaller than half, we have positively correlated increments. And if h is greater than half, we have negatively correlated functions. By comparing the correlation functions of the fractional Brownian motion and the correlations of our noises, our random forces, we can obtain the proportionality coefficients, and we can also obtain a relationship between the order of the fractional derivative and the Horst exponent, which is alpha equal to minus 2h. So using these facts, we can obtain a discretized expression for the fractional Langevin equations. So first, we integrate the whole equation. So we see that now the recursive expression is not going to depend anymore on the increments of the Brownian motions or the fractional Brownian motions, but on the Brownian motions. So we see that it's proportional to a Brownian motion and to a fractional Brownian motion. We can also use the relationship between the Riemann-Liouville derivative and the Caputo derivative to get rid of the first order derivative that it's in the definition, because the Riemann-Liouville has the derivative outside the integral, and we just have an integral operator that can be discretized using the mean value theorem, the extended mean value theorem. So with these ingredients, we obtain this recursive expression, and we can use it to obtain numerical solutions. So we use both methods, the analytical method and the numerical method, in order to study the anomalous diffusion regimes of the system. So for the inequilibrium noise case, we can obtain the mean square displacement of the system directly by integrating the relaxation function. This can be shown by using the relationship between the memory kernel and the correlations of the noise. And the only effect on the expression that we already obtained is to increase the order of the Mittag-Leffler function. So we see that when we test the results, the analytical results are the dotted lines, and the colored lines are the numerical results with the confidence intervals of 95%. We observe that they converge very well. And for the zero linear friction case, the out of equilibrium noise, we see that there are two contributions that affect the mean square displacement. So the first one is the contribution from white noise, which is obtained by getting rid of the second integral that appears in the mean square displacement using the Dirac delta, and the contribution for color noise, which is kind of similar to the contribution to the previous case, that can be as well obtained using the relationship between the color noise correlation and the memory kernel of the fractional operator. So again, we obtain a Mittag-Leffler with an order 1 times higher than the previous order. And when we test the results, we find a very good convergence as well. So from the point of view of physics, we observe very interesting properties here. So first, we observe that for both cases, we have a dominant universal ballistic behavior in the short term, which is driven by the inertia of the system. And in the long term, we find a dominant subdiffusive regime proportional to the T to the alpha. So this is dominant in both cases. We can observe this by asymptotically expanding the results for both expressions. But interestingly, we see that in the zero linear friction case, certain periodic orders, certain oscillations emerge for small orders of alpha. So when we dig into this periodic time order, into this emergent periodic time order, we observe that, well, first, in order to have it, we need to have zero linear friction. So we are in the second case that we studied that I presented in the microscopic derivation. And we observe that this occurs for small orders of alpha. So approximately when alpha is smaller than zero point 0.1, we start observing well-defined oscillations. So for this study, we have three different cases. So first, we have the case in which we switch off the white noise. So we only have contributions from the color noise. So that means that eta 1 is equal 0. In this case, we have that fluctuation dissipation is fully preserved because we only have a color noise with correlations proportional to a power law, and we also see that the fractional memory kernel is proportional to a power law. So we have fluctuation dissipation. We have an inequilibrium ground state because the system is coupled in equilibrium to a set of degrees of freedom that are modeled using a harmonic oscillator, which is perturbed around a minimum energy state. And we find a periodicity in the oscillations proportional to 2 pi. This periodicity can be tested using the Fourier fast transform technique. So we can see it in the first line of plots, the results from the Fourier fast transform techniques. And we observe that, in fact, they saturate around 2 pi. In this case, we find also a trivial limit case when alpha goes to 0, which behaves as a time crystal. So a time crystal is nothing more than having these oscillations perpetually in time. So they are not damped, as in the case when alphas are different to 0. For the second case, when we have eta 2 equals 0, we have only contributions from the white noise. So that means that fluctuation dissipation is broken, and we obtain a periodicity proportional to pi. This is a very interesting case that was previously identified by Robin and Christiane as a time glass. So in general, the broad idea, because I think that at this point, Robin already mentioned a lot about time glass, is that we have a periodicity proportional to pi characterized by the repetition of a linear behavior that then saturates into a plateau. So we find this in time, replicated in time, and it means that the particle displaces from the position and then it gets trapped by a cage. So we have kind of an finite cage landscape in the system. And for the third case, we find a mixed phase with contributions from both noises. So in this case, we see that the periodicity deviates to square root of 2 times pi, that the color noise is in equilibrium in the system, but we have perturbations from the white noise. So what we observed is that, again, the plateaus kind of emerge, but then they are perturbed by the oscillations of the color noise case. So it's kind of a mixed phase between this transient effect identified for the color noise and the time glass identified for the white noise. So let me finish with the conclusions and the outlook of the talk. So just to recall, we solved the fractional Langevin equation with white and color noise for two cases, the in equilibrium case and the out of equilibrium case. And everything can be obtained in terms of the Mittag-Leffler function. So for the in equilibrium case, we use the Prabhakar-Mittag-Leffler function, and for the out of equilibrium case, this reduces to the conventional two-parameter Mittag-Leffler function. We also obtain numerical solutions using a discrete expression, where the noises are modeled using fractional Brownian motion, and we observe a very good convergence between the numerical and the analytical methods. So from the point of view of physics, we observe very interesting regimes. So first we see that a subdiffusive dominant regime emerged by the effect of the fractional friction, where the mean square displacement is proportional to t to the alpha. But we also observe emerging periodic time orders for small orders of alpha and zero linear friction. So in this case, we see three different regimes: a transient order that it's driven by the action of color noise and with a time crystal limit case, a time crystal trivial limit case. We also observe that the time glass is caused by the action of white noise, and we find a mixed phase with a superposition of both noises. As an outlook, a very interesting direction of work will be to study if this type of periodic time ordered phases can emerge from more general noises and also from distributed order operators, and also to see the properties of the relaxation of the system, if there is any type of ergodicity breaking in the thermalization of the system. Thanks for your time, and let me finish with this. I'm looking forward to reading your questions.
Thank you so much, David. So excellent presentation. And we have
Thank
a
you.
question in Spanish for you from
Perfect.
Adrian. Sorry, I don't speak Spanish. So
No, it's fine. So yeah, just to have the general idea, someone is asking maybe for the people that don't speak Spanish as well, uh, between the attendees. So someone is asking if I already studied the stability of the solutions in the numerical approximations that we implemented for this work. Um, so maybe I'm going to continue answering in English just for the audience, general audience. So no, we haven't done it, but this is a very well-known recursive scheme in fractional in the solution in the numerical solutions of fractional operators. So there are two approximations here. So the first one is to approximate the fractional operator using something that is called L1 and L2 schemes. So these schemes have already been studied uh, in deep, and the stability of these solutions, it's usually good. And we also approximated the noises using Brownian, fractional Brownian motion, but since we are integrating, we are not using the increment, which could be a bit more unstable than using the proper integral of the increment, which is in principle from the point of view of stochastic process should be a smoother function and a bit better behaved. So in that sense, it also helps for the stability of the solutions.
oh, okay. I have a question. What computer language did you use to the numerical simulations?
I used Python,
Oh,
which is not the most efficient. We actually started working with a Monte Carlo
okay.
scheme just to solve the equations by brute force. The algorithm used to work well, so the solutions were actually converging to the analytics, but it was too heavy, even if we coded it with another student of Christiane. We
Hmm.
made the implementation in Julia, which is way faster than Python, but it was not fast enough. So then we moved to this recursive scheme, and it works very fast. So for this case, it's enough to use Python. Maybe for a heavier algorithm, we should have to rethink the language to use, but for this case, Python is perfect.
Oh, nice. We have a lot of congratulations from Professor Edmundo.
Thank
Congratulations
you.
for Professor Sandro. Beautiful work and lecture. And Adrian say thank you for you. And I have a lot of congratulations. And thank you so much, Davi. David, I don't know.
David.
Then David, I'm sorry, it's a great presentation. And now we have another presentation at 11. And thank you so much. Thank you, everybody.
Okay, thank you so much as well for the event. I have learned a lot in these 3 days, and I can imagine that I'm gonna learn even more in the next few days. So thank you so much.
You're welcome. Thank you, guys.
Bye bye.
Bye bye.